This technique is column chromatography. What you're looking at right now is a column that is set up in a hood with a ring holding it up, and the tube leading off the top of the column goes to a manifold and then to an argon tank. This is the setup for a normal flash chromatography sort of column, which is to say what we do is we put all of the components in the middle of the column and then we apply pressure to the top to force things through. What you'll actually be doing is a slightly simpler stripped down version of a column. That is what we do when we have a relatively small amount of sample. Rather than using gas pressure from argon to force it through, we will instead apply pressure to the top using the bulb and just squeeze through. Still flash chromatography, a little bit simpler, a lot cheaper. We'll talk about how we set these things up. The principles behind column chromatography are essentially identical to the principles behind thin layer chromatography. Fundamentally, what we are trying to do is exploit polarity differences between compounds in order to separate them. What we've done so far is separate them on a TLC plate, which is to say a two-dimensional surface. What we're going to do is now exploit the same principles to separate them on a column. In order to run a column well, you first need to run TLC plates in order to identify how to separate the compounds from each other. You need to know how the compounds behave on silica gel before you can try to run a column. This is fundamentally the same reaction that I was describing in the TLC series. What I have here is 3 different compounds on each TLC plate. The desired thing is going to show up in the middle. The reaction itself, after I quenched it and isolated the material, and now I have a goop that contains several compounds and needs to be separated, that's in the middle. The 2 starting materials, SM1 and SM2, are now potential impurities. This is a general lesson. Once you are trying to isolate the stuff that you care about from a reaction, everything else is an impurity, including the good starting materials that you started with. So this is SM1, or the aldehyde. This is SM2, the ketone. And the products are in there. Moving from left to right, the concentration of ethyl acetate in the solvent goes up, and the concentration of hexanes in the solvent goes down. Since ethyl acetate is relatively polar, what you have is an increase in polarity from left to right. Had I not told you that, you could still understand that that must be true looking at the TLC plate. Relatively low polarity means that the compounds don't move. Relatively high polarity means that the compounds move to the very top of the plate. Intermediate polarities, and the compounds move somewhere in between, and you can tell that this is more polar than this solvent is more polar than this, and so on. All compounds move further up the plate with increasing polarity. All compounds move less with decreasing polarity. Looking at 0%, this first TLC plate, what you see is none of the compounds move. In other words, could I separate the compounds from each other? It's 0% ethyl acetate, 100% hexanes. The answer is, of course, no. Since they do not move, there is no separation, we cannot get them apart from each other. In 10% ethyl acetate, 90% hexanes, what you see is a large spot down here. Presumably, this is the spot that I care about. There are incredibly faint spots up there, very difficult to see, and those are presumably impurities that I need to get rid of. This impurity appears to be the same as SM2, starting material 2. This starting material 1 does not appear to be present, but whatever impurity was present in starting material 1, that is present. In other words, what I'm going to have to try to do is to separate the stuff that I don't want from the stuff that I presumably care about. It appears as though using 10% ethyl acetate hexanes will allow the impurities to move off of the column well in advance of the desired stuff. It does not appear as though my stuff will move very much in 10% ethyl acetate hexane. So I increase the polarity more to 20%, and I learn that everything moves more, including the compound that I want. Notice that the separation between the stuff that I want and the stuff that I don't is actually larger in 10%, and they start to compress together in 20%. Therefore, it makes sense for me to start this column in 10%, try to remove all those things, and then elute that later. So I start in 10%, then bump to 20%, and once this has come off the column, then I can move this up. If it's not moving fast enough for my tastes, I could then go to 40% and move it even faster. If I switch to 80% ethyl acetate hexanes, everything moves up the column immediately. The conditions that make the most sense for column chromatography are the ones where you have the widest separation between the thing that you want and the things that you don't. This is the most fruitful avenue to be pursuing. So my column chromatography, I will be using these intermediate polarities. Once the TLC work has been run, the next order of business is to prepare the column for chromatography. In other words, to pack the column. What this requires is to create a surface for the silica gel to sit on. If you have an expensive column, then there's a frit, as in a fritted funnel, and you can just simply pour in silica gel on top, And what that allows you to do is then just run the column directly. However, that's a relatively expensive solution, and there are cheaper solutions. This is the sort of column that we use almost all the time. In order to run this column, all we need to do is introduce a cotton ball into the bottom of the column. That will then have this, we will then have the stopcock sit on right below that ball of cotton. So the cotton is now a surface that we can pile stuff on. The next order of business is to add sand to the column to provide a surface for the silica gel to sit on. As sand is relatively coarse, it provides a nice surface, and all you really do is add just enough sand to create that flat surface so that we can put the silica gel on top. There are essentially two normal ways of introducing the silica gel at this point. Dry packing essentially means that you just simply pour silica gel into the column, later introduce the solvent. So now I've introduced some silica gel. If I want to now prepare the column for chromatography, all I really do is go ahead and add solvent and allow the solvent to filter through. This is known as dry packing a column, and this is a totally normal and standard way of doing it. You will note that the solvent moves relatively slowly through this column because we're relying on gravity to do it for us. You can speed this up by means of a rubber bulb. Simply by putting pressure on top of the column and then squeezing allows us to force the solvent through much more rapidly. Once the solvent is near the top of the silica gel like that, then what you can do to equilibrate the column is to take the beaker of solvent that has run through and then pour it through again. Do this several times. What you are looking for is the absence of bubbles in your silica gel, and that requires a very fine attention to detail. You're looking to make sure that this silica gel has a uniform appearance. As mentioned, this is the dry packing method, and this is one of the two standard ways of doing it. The other way is known as a wet pack method. The difference between the two methods is largely one of personal preference. There's advantages and disadvantages to both, and there's a fair degree of superstition that essentially amounts to what has worked for you in the past is what you will continually do in column chromatography. The way it works, rather than introduce the silica gel first, what you do is you put solvent in some container, and then you add the silica gel to that solvent and create a slurry, which can then be poured into the column. One significant advantage to this way of doing things is you're less likely to inhale the silica gel as you do it. It does, however, create messes in other ways. In any event, what you simply do is pour the slurry into the column. You can use additional solvent as needed to transfer the slurry into the column. One disadvantage to this method is it seems to create a fair amount of mess, and there's a lot of silica gel that needs to be cleaned up after you go through it. Once the silica gel has been transferred on top of the column, you can then force the solvent through. You can force the solvent through much as before, and you end up in the same place. As I mentioned before, there are advantages and disadvantages to packing columns this way. My own personal preference is essentially a hybrid between the dry pack and wet pack methods. Given the amount of material that I'm going to try to separate, I require a slightly fatter column. In other words, I'm going to use this relatively large one, and I'm going to pack using the hybrid method I've described. Solvent I've introduced first into this container so that I can go ahead and essentially dry pack and wet pack simultaneously, pouring in the silica gel on top, and as that silica gel goes and mixes with the solvent and has the effect of generating a slurry. I can then add additional solvent to the top of the column in order to assist in the formation of the slurry on the inside of the column. Then I can force gas through the system in order to help remove the bubbles. One of the things that I can do to remove bubbles at this stage is to agitate this column, or even to stir this column. Once I've attempted to remove air bubbles, then I can simply open the stopcock and allow it to drain out, much as the columns that I've already demonstrated on. Once again, this will happen relatively slowly until I increase the pressure on top. Standard flash chromatography requires me to force argon gas through the system using an adapter, a gas adapter. I simply clamp the adapter in place and then increase the argon pressure, and solvent will flow out much more vigorously. Once again, it is always a good idea to stop the flow rate when the solvent is nearing the top of the silica gel. Equilibrated, so it looks uniform throughout the silica gel surface. Then you allow the solvent to drain down to the very top of the silica gel, and even possibly allow the very top of the silica gel to become ever so slightly dry. This is the only time when you will allow the silica gel to become dry at all. Now in preparation, you must dissolve the compound to be separated in the most minimal amount possible of solvent that is the least polar you can get away with. Once the mission has been accomplished, then it's time to load the compound on top of the silica gel. This means to transfer the compound gently on top of the silica gel so as not to disturb the silica gel. Once the compound has been transferred on top of the silica gel, then open the stopcock and allow it to drain through. You may now use a very small amount of extra solvent to assist in transferring the rest of your compound on top of the silica gel as necessary. But again, the minimal amount of solvent possible with as little polarity as possible. Once the rinse has been transferred on top, then open the stopcock. At this point, it's usually standard procedure to put additional sand on top of the silica gel so as not to disturb it when you pour in additional solvent. But now we are essentially ready to run. Given my level of expertise running columns, I usually prefer not to put the extra sand on top and simply pour on directly and then run. I am now ready to start running the chromatography. As you can see, the solvent is in the reservoir. We also have the ability to increase the gas pressure on top of the column. The other thing I personally find useful to do is to find some way of rigging up test tubes such that I don't have to hold them myself, giving myself a third hand, if you will. Now we're ready to run, and from this point on, anytime I open the stopcock, I will collect the liquid that comes out in a test tube. And then I will take those test tubes and start setting them in these numbered racks as we go. So here we go. Open the stopcock, increase the gas pressure. And as the test tube fills up, I transfer it out. And keep going. Once the solvent nears the top of the silica gel, then you stop. In this particular case, I went a little too far. The silica gel is now dry up there, and that is less than ideal. In any event, once the solvent has reached the top of the silica gel, then there's a decision point. Do we change solvents or do we continue on? In this particular case, I happen to know that my compound is brightly colored. It is the yellow compound, and it's currently sitting here at the top of the silica gel. Since it has yet to move, as expected, given what I packed the column in, now it's time to increase the polarity somewhat, and I will change to probably 10% ethyl acetate hexanes and run through another slug of 250 milliliters or so, another 7 or 8 test tubes, before I then change to a different solvent. I have now reloaded the column, and I'm ready to add some more. Once again, what I'm going to do, open the stopcock, increase the gas pressure, and keep collecting test tubes. The higher the flow rate, the faster this goes. And there you have it, a reasonably short, relatively friendly column. You can even tell, barely on camera, that some of these test tubes contain colors, and some of them do not. But the question ends up being, which of these fractions contain the compound that you want? Keep in mind that my starting material and my product are both highly colored, and specifically yellow. When I see yellow fractions, that could be either the thing I want, or it could be the starting material impurity. There's only one way to find out, and that's TLC. Which means that I need to run a TLC on all 48 fractions. Even a relatively straightforward and friendly column like this one still requires a huge amount of TLC in order to figure out where the compound is. Once I know where the compound is, which of these fractions contain the compound, then I can combine them and remove the solvent. You've seen TLC before, so I won't belabor the point too much. But I do want to point out that yes, all 48 of these fractions need to be assayed by TLC, which means that we're going to put a lot of them on a given TLC plate. I'm going to do all 48 of these fractions on 4 plates. And the other thing I'll point out is that I want to be relatively quick about this, which means that I'm not actually going to wash the TLC spotter in between. I simply dip, place, and blot out the excess onto the paper towel, and dip, and place it, and blot it out, and keep going like that. The reason why is all I'm trying to do is find out whether the compound is present. If I discover that the compound is present and it looks like I have some impurities because I'm not washing the TLC spotter, then I have plenty of time to go back through and run another TLC plate after that if I need to. And it's dramatically faster if I don't wash the TLC spotter between every test tube that I place on the plate. So you just try to burn through these as quickly as you can. I really wanted a reminder of 2 points. One, it's useful to have a known on a TLC plate, which I have here marked by a small K. That way, if you'd like to compare what you're seeing to what you've seen before, you can. And 2, that it is possible, and usually a decent idea, to run multiple TLC plates in the same TLC chamber at the same time. And there we are. We have all 48 test tubes now have been reduced to TLC plates. This top TLC plate is boring. It's the first one. It contains possibly some junk, but nothing of real interest. This line of compounds right here, this line of test tubes, is starting material 2, the ketone, coming through. This right there is the product that I'm desiring. I know this because this is one of my knowns. And it's useful to have this on a TLC plate for direct comparison, so I can say, yeah, I'm not interested in that. I am interested in that. So you can see the compound that I actually care about starts coming out somewhere in here. And in fact, what I've now learned is it's 2 separate compounds. This compound is an impurity, and this is the desired compound. So I'm really interested in that compound right there. And for the purposes of rotavapping down and isolating my material, what I will do is select only the test tubes that contain the desired compound, which is to say these guys, these 2 test tubes right here, are mixed fractions. I'm now going to cam stain these so you can see it under slightly different conditions. And this is why we do cam stain versus UV light. I was just telling you that I was interested in the compounds that were here. Now that I've done a cam stain, what I see is that there's a very UV active spot that's hanging out right there that doesn't amount to very much when looking at a cam stain. And in fact, the compound that I'm interested in, based on the known, is right here. And therefore what I'm interested in is these fractions and not so much these other ones. So what I'm going to take for the purposes of evaporating off are fractions, the last 3 fractions here, so that would be 36, 35, 34, and then the first 4 or 5 fractions here, 37, 38, 39, 40, 41, or thereabouts. Combine them all in one single round bottom flask, and then rotary evaporate it off. And that will give me the compound that I want. Notice over here there's less confusion. What seemed like a very heavy UV active spot is a very light spot by cam. That's not unusual. Not much going on in this plate. Junk that we don't care about there. Desired material is all there. So I simply combine those. All fractions of interest are now in this round bottom flask, ready to be evaporated. And this is the machine that we use to remove the solvent from the round bottom flasks. And there's the round bottom flask with the solvent spinning, and we're heating it up. It's slowly, vapor goes up here into this condenser, which cools it down, and it all comes out here. And so it's a means of transferring all the solvent away from the compound that we care about. And when all is said and done, what you'll be left with is just the compound itself as a yellow solid or perhaps a yellow liquid. Once we have successfully removed all of the solvent, what you'll be left with is some residue, and we don't necessarily know what that is until we take an NMR. Dissolve it up in chloroform D, take it downstairs to the NMR instrument, stick it in there, run a few scans, and try and figure out what we have. After all, until you know what you've made, synthesis is not yet over. But this is essentially chromatography in a nutshell. Separation of the desired component away from the other stuff.